Yeah,
It's
cool.
recorded.
Cool, cool, cool,
Okay.
cool. Yeah, sorry for the delay, but eventually stuff is settled down. Okay, cool. So everyone can hear my voice, right? Okay, cool. Yeah, okay, cool. So my name is Mox, and I'm currently doing my third year electrical engineering. So I did this course last year, this term, and hopefully I still remember something to help you guys through it. I think for your midterm exam, it's gonna be covered the first two topics, which is the amplitude modulation and the frequency modulations. And so when we talk about this course, right? So it's all about the modulation stuff. So what is modulation? Or what is two very important things we have to be engaged into modulation is your message signal and your carrier signal. So what essentially modulation refers to is like, if we're trying to transmit your like any analog signal, right? So such as your speech, your voice, it only behaves like very low frequency. But the low frequency is not enough or is not efficient for transmission, right? Normally the days, the channels they are being operated at very high frequency. So that's the reason why we require a very high frequency carrier signal to carry this message frequency, and then we can transmit efficiently. That's the reason why we require this carrier signal to transmit the message signal. So for the amplitude modulation, so I'm going to go through like okay, so basically for this session, the way I'm going to organize it, I'm going to went through the content first, and I'm going to go through the past year midterm exam paper. So for the content first, I'm going to go through the amplitude modulation and the DSB, SSB, and then the frequency modulations. So start with the amplitude modulation, which is the very common way to do the modulate. So what is the basic format? It's ST equals to AC times by 1 plus M cos omega MT and times by cos omega CT, right? So I'm pretty sure all of you guys have already done your lab too. The process looks like you're gonna send your mesh signal to a multiplier, which the multiplier has actually you're gonna to send to adder first. You're gonna add some DC constant, probably just DC equals to 1 volt, and then send it to a multiplier, and the multiplier gonna have another carrier wave. It's gonna be cos omega AC cos omega CT.
Maybe they can't see it.
Oh yeah, sorry.
Turn it maybe horizontal.
Yeah. And then you gotta go ST, which is equals to AC times by 1 plus M cos omega M cos omega CT. So what does the amplitude modulation signal looks like? So normally it looks like a very huge envelope and with very high frequency carrier which been containing it. So the envelope usually is encoded our message, right? So the shape of our envelope essentially is our message signal. When we talk about the amplitude modulation, one very important concept has to be involved, which is the modulation index, which is this M. So this M determines your shape of your envelope, right? What happens if your M is smaller than 1? It means that you successfully form like an envelope. And you have to keep your M small as 1 to make sure you can use envelope detection to detect your demodulated signal, right? So how could this M like mathematically influence your signal? Is like we have to look at the formula. The M is equals to A max minus A minimum over A max plus A minimum. So if you look at the diagram here, the A max is the peak of your envelope, and your A minimum is the trough of envelope, right? So if you think like this way, this is the case where your envelope is successfully formed, right? your AM and your A minimum are both like a positive integer, right? They are both positive. And when you do the subtraction between two positive number, A max definitely greater than A minimum, right? So this has to be like a positive value, but it's definitely smaller than the sum of two values, right? So that makes sense because M eventually in this case will be smaller than one. If we look at M equals to one cases, so M is equal to A max minus A minimum and over A max plus A minimum. At this case, is the waveform gonna look a little bit different because you're gonna see the envelope gonna touch the edges of your x-axis. So in this case, this is your A max, right? And your A minimum, it tends to be zero. It tends to be zero. And when you look at your denominator here, right? Your A minimum also gonna tends to zero, which in this case, your M is only A max over A max, which essentially equals to one. So if you look at the M, which is smaller than one, which is bigger than one, which in this case, your envelope cannot be successfully formed, which has an issue called phase reversal. So if you look at this case signal waveform, it will be something look like this. So this time your A max is still a positive number, but your A minimum tends to be a negative number, right? So a positive number minus a negative number will tends to be a very big positive number. But a positive number plus a negative number will tends to be a small number. So essentially your denominator is doing like a subtraction. That's the reason why you have M is greater than one, right? Because your numerator definitely gonna be bigger than your denominator. Anyone got a question on this? Okay, cool. So that's like how we understand the modulation index and the envelope waveform, right? From the mathematical perspective, I think it's better to understand like in this way. Oh, oops. Yeah, cool. Yeah. So the amplitude modulation, yeah. So like after we go through the modulate signal, like we're gonna look at how does signal be demodulate, right? So we'll talk about the AM demodulation. There are two ways to demodulate a signal. The first way is called envelope detection. The second one is the coherent detection. And we're gonna look at the mechanism behind two of them separately. So when we're using envelope detection, what we're essentially doing is we're gonna use structure like this. So we have our V, and this is our we got a dial which is forward biased. I'm gonna have a capacitor over here, and this is your essential V output, and this is your V input. So the idea to look at is if this is our modular signal, right? Yeah. And also it's our V input. So you can think about like this V input here is essentially our modular signal. Right now, we're trying to use this kind of structure to detect our shape of envelope, right? Because all the information are being stored or encoded into this shape, into this envelope shape, right? So look at the V out, right? So by start, because you're sending this signal to your forward to this diode first, and then it will cross the capacitor, right? So essentially, this capacitor, I'm gonna write it T. So essentially, because this diode will be forward biased, and also you are sending like an increased signal, right? So this diode will be forward biased, so the message signal will be passed, and then this diode will be charged off. So it's gonna follow the trend of increase. So let's give this point volts, let's say 0.5 volts. And at this peak value, the VO here is equal to 0.5 volts. And probably your input also equal to 0.5 volts. But after this second, right, it's gonna drop because this is a peak, right? So after this point, the signal, the voltage output gonna be dropped. Let's say probably drop to 0.45. Let's just randomly say that's 0.45. So if the voltage here is still 0.5, but your input voltage is dropped to 0.45, what does that mean? That means this diode is going to be reverse bias, right? So your signal cannot go through this diode anymore, and your capacitor going to discharge, right? So at capacitor side, you're going to have a drop here, right? Because it's not going to be charged anymore. It's going to discharge because this diode is no longer forward bias, it's now reverse bias, so it's going to drop, right? So the whole system going to follow this cycle again, right? So it's going to increase and decrease, increase, increase, decrease, increase, decrease, and eventually form this kind of zigzag, right? But this is a good thing as long as we kind of get our envelope shape back, but it's kind of it's not smooth. So we're gonna pass through this V out into our low pass filter. So the low pass filter essentially here is playing a role of get rid of those zigzag and trying to smooth the shape, because the low pass filter will get rid of the high frequency component, right? So this zigzag usually being caused by the high frequency noise or high frequency interference. So we try to use this low pass filter to get rid of those kind of things, and then we can eventually smooth our envelope. So this is about envelope detection. So very important for envelope detection is we have to look at modulation index. So it only works for when modulation index is smaller than 1, right? So if it is equals to 1, we can still kind of reform it, but it's on edge of getting your envelope distorted, right? So if your M is greater than 1, which means you're gonna have like a phase reversal. You're gonna have a phase reversal like this. And when you're trying to reform the shapes here, essentially the envelope detection gonna detect this waveform. It's gonna detect it like this way. It's gonna detect the green section, but you know that's not the envelope, right? That's like you only like go through like the top, but actually the envelope should goes down, right? But it does not goes down. So like you only look at like the wrong waveform. It's not what you're looking for. So envelope detection only look at your, is really important to look at if your envelope is successfully formed or not. If it's distorted, you cannot use envelope detection anymore. And that's the stage we have to come to our second methodology, which is the coherent detection. So what is coherent detection? Essentially, we are putting our ST into a local oscillator, which gonna have a signal called cos omega CT. So this omega C is essentially equals to your carrier frequency, right? We want the local oscillator to generate a signal has the same frequency as your carrier signal, and we will see why. And then we're gonna pass through it through a low pass filter again, then we can get our message signal. So the idea looks like, if we assume our ST is equals to A times by 1 plus M cos omega N T times cos omega CT, right? And if we're gonna multiply with your local carrier frequency, local carrier signal, which is cos omega CT, right? So it's gonna look like cos omega MT and times by cos square cos omega CT, right? And you're gonna have so this is essentially a trigonometric identity, right? So when you square it, and you can rewrite into 1 plus cos 2 omega CT over 2. And eventually, when after you expand this term, and I think you will eventually get your, just let me expand it. I'll probably we don't have to write this form down. We can probably just write it as an empty because we don't really have to know like the real form of it. It's gonna be 1 plus 1 plus cos 2 CT is AMT 1 plus CT. Okay, so essentially what we want is only this section, right? Because this section is only like your carrier frequency, right? It's like your carrier frequency and your local oscillator component. This section is the same way, right? So we don't want this two section. That's the reason why we put through this signal into like a low pass filter. And we can get rid of this two high frequency components. And that's the way how we can reform your signal. Oops, yeah. Anyone got a question? Yeah.
What would be the cutoff frequency that
it has to be like so we have to look at real specific cases, but in these cases we have to let our cutoff frequency to at least be greater than your message signal frequency, but it has to be smaller than 2 omega c because we want to get rid of the 2 omega c component. But we have to keep our message frequency. So let's say if your message frequency is equal to 5K hertz, right?
Yeah.
And your 2 omega c is like very big. Yeah, probably like 20K, yeah. Right? And your low pass filter gonna look like this, 5K, negative 5K, and your 200K definitely is outside the range. Will be cut off. That makes sense?
I also have another question.
Yeah.
Where would we be able to access the recording for this session?
Access,
Post it.
yeah.
Okay.
Not on Facebook, but if you sign up through the link, then you will get the recording. They will send it to you. I think a link to the recording.
I'll take a look at that.
Yeah. Cool. So that's the way we actually get to coherent detection. So this one does not actually really care about your modulation index, because essentially we're using like a mathematical perspective to solve the problem. We do multiplication, we do trig identity, and then we can realize that the expansion is involved like different frequency component, and then essentially we just pass the signals through like low pass filter, and we can get rid of the component that we do not want, and to keep our message components and reform it. So that's kind of the trick we're gonna use like through the course. Also in your exam, I think it's gonna be some of the questions. You're gonna do like some multiplication, and then you're gonna look at the frequency component, and you're gonna think like what low pass filter you're gonna choose, the range of it, right? Because you want to get rid of the part you don't want, right? So I'm gonna go through some questions sort of like this later on. Cool. Yeah, but there's an essential problem, potential problem of this coherent detection is, even though you can use it regardless of your modulation index, but there will be a problem called phase shift. It will be a problem called phase shift. So I think if you did your lab straight, right, you use your coherent detection to demodulate your SSB and DSB. In your lab menu, you are asking to pass your local oscillator signal to like a phase shift. So you're gonna have a phase shift called like phi, right? So the reason we want to use this phi is because in reality, your local oscillator is not 100% synchronized with your carrier signal. So we cannot say that your local frequency is just cos omega CT. It's definitely going to have a phase shift over there because your transmitter and your receiver, they are not at the same location. So when you're trying to generate two signal, they can't be 100% synchronized. And this is kind of like a non-ideal case. But in your lab, right, so you are literally generate the signal from like the same block. So they have to be in phase. But in real, like in the real industry, it's not that case, right? So you're gonna have a phase error over there. And the negative downside of using coherent detection is you're gonna to use the phase lock loop, a phase loop block to get rid of that phase error. And because this phase error gonna cause a really huge attenuations, especially in your DSB to your message signal. Yeah, so that's the point I'm probably gonna mention because but I think if you guys go have already done your lab 3, you probably you should probably know about like this, how does this phase error gonna affect your demodulated signal. And the next thing I'm gonna talk about is the spectrum. Right. So the frequency spectrum or the frequency analysis of the signal is really important because if you look at your analog signal, right, you can't really see the pattern or whatever. So let's say if this is your analog signal, right? What can you know about this signal? You do not know the frequency, you do not know like the period. If I just give you like a really, if I don't give you any other information, right? So you can only know this the details or the characteristics of this signal if you put into like oscilloscope, right? You can know its frequency. But spectrum can tell you like a lot more. It can tell you what is the frequency component, and you can do a more detailed understanding if you look at the frequency spectrum. So what does like a normal amplitude modulation spectrum looks like? So if your message signal, let's say your MT has a frequency of 5 kHz, and your carrier frequency is sort of like 100 kHz, right? Because we're trying to make sure our carrier frequency is way large than your message frequency, right? This is for avoiding the spectrum overlapping because if it's too close, it's gonna have an overlapping there, which will distort your signal. So your MT, if you look at this, your frequency spectrum, it's gonna look like, okay, I'm also gonna assume if it is, probably I'm gonna assume it's like a sinusoidal. It's probably just like a cosine. I'm gonna write it a cosine omega mt, and f is equals to 5 kHz, and omega m is equals to 2 pi times 5 kHz. So essentially, your carrier frequency is 100 kHz, right? So your carrier frequency 100 kHz. And if you look at your ST is equals to AC times by 1 plus cos omega mt times cos omega CT. After you do the Fourier transform, you're gonna have two components which look like this. You're gonna have your negative FC and your positive FC, right? And it's gonna look like this, two triangle. When actually when you do the lab, you're gonna see like a spike. It's gonna be FC, negative FC, positive FC, and you're gonna see this kind of spikes over there. And this part is FC. Oh, yeah. It's FC plus FM. And this part is FC minus FM. And this is negative FC, so it's going to be at negative FC plus FM. It's going to be negative FC minus FM. So this is your amplitude modulation spectrum going to look like. Anyone got a question for that? Oh, good. Yeah. Yeah, okay, cool. Yeah, so if you look into your DSP spectrum, it's going to be a little bit different to the amplitude, the modulation spectrum, because for the DSP, the reason why we're using DSP is we don't want the carrier frequency components, because carrier frequency component essentially will cause spectrum density efficient to be a little bit lower. So that's the reason why we're trying to get rid of the to get rid of the carrier component. And the ST will look like AC times by MT, apologies, MT, and times by your cos omega CT. And your spectrum gonna just looks like negative FC plus minus FM and FC plus FM. It's gonna be FC minus FM and FC plus FM. So this is gonna be your DSP looks like. It's gonna be how does your DSP spectrum look like. And if you look at your SSB.
Question.
Yep.
Excuse me, sir. Just going back a page.
Yeah.
I was just wondering what those triangles represent.
The triangle is like the real spectrum, right? Because like you cannot actually observe the spike clearly like this. You always got noise, right? So like it's not ideal to have like a spike. So normal way you can probably just like express as a triangle or a rectangle. Yeah.
It's more like a range.
Yeah, it's like a range. Exactly. It's like
Thank you very much.
Yeah. Yeah, so if you look at your SSB signal, right?
Sorry.
Yeah.
Can you go back to the double sideband spectrum for 1
Yeah,
second?
yeah. This one, right?
Okay, okay.
Yeah.
That's it.
Yeah, okay. Yeah, so you don't have the carrier at the middle, right? So you get rid of the carrier components. And if you go to SSB, it's gonna have two cases. One is called lower sideband, and other case is called upper sideband. So the lower sideband, you only take the lower component, which is negative FC plus FM and FC minus FM. And for the highest, for the upper sideband, you only take like negative FC minus FM and FC plus FM, right? So SSB and DSB, they have really good spectrum intensity transmission because you are having very small amount of component which encoded your signal message. But the downside is you have to use more channel for modulation. So it's kind of like a trade-off. So if you wanted to save your transmission efficiency, but at the meantime, you're gonna like spend more channels to do the demodulation, right? To do the modulations. Yeah, and both DSB and SSB are we using the coherent detection to demodulate, right? But the same issue comes over and over again is you have to solve the phase error issue. And I think SSB, it has very little effect on the phase effect on the phase error. So it only will cause your demodulated signal to have like a phase shift, but will not have a very strong effect on the amplitude attenuation. While for the DSB, because you have your message signal is like half A times MT times cos phi. So this is your DSB demodulated signal. You can see there's a cos phi term there. So this cos phi term is gonna strongly affect your amplitude of the message signal, right? I think in your lab you also play with that term, right? So if you have this phase almost equals to 2 pi over 2, you're gonna hear like very small volume of voice. It's because when the phi is close to 90 degrees, this one is close to 0, and which will attenuate your amplitude quite a lot. But for SSB, I think MT is like half, it's like cos with omega MT plus like a phi. So this phi is inside your message signal, which only causes your message signal to have like a little bit phase shift. But because you will not have like cos phi term outside your expression, so will not actually affect your amplitude a lot, right? And in order to solve this phi issue, we're gonna use the PLL, which is the phase locked loop. And we're trying to eventually minimize it, right? You guys know what's the PLL, right?
Not really.
Not really. Okay, cool. Cool. I'm gonna go through it. So yeah, so the PLL is like essentially gonna have your, okay, I think I got a flow chart in the lecture slide.
Do we have to know that zipper of the heads or something?
You probably have to go through some of them, but I don't think that's gonna take the very big percentage of the, as long as for me, we didn't have, yeah, we didn't like, yeah. Yeah, let me just find the block. Yeah, so this is the phase lock loop, right? So essentially you are putting your input signal. Oh wait, actually it's, yeah, you're essentially gonna put your input signal into what we call a phase detector and then go to like a loop filter. And then it's gonna have like a feedback to a block called VCO, which is voltage control oscillator. So this voltage control oscillator essentially is like a frequency demodulation block. It's doing a frequency demodulations, and you're gonna have like a V out output, and essentially this V out output is gonna compare with your input phase, and then it's gonna generate an arrow. So the arrow is, I think the arrow is this one. So this is your arrow signal. So let's say, just give me a second. Let me go to so this is a general block for PLL, right? So you send your modulate signal into a phase detector. So let's assume your initial modulate signal is ST equals to AC times cos omega CT plus phi, right? I'll probably would just ignore this phi first because we're trying to make our terms become a little bit simple. Just write it as a AC times by cos omega C. Probably with omega m. Yeah. I'll probably just wait a file with it. Never mind. And this, and then the reason why we're using like a different expression for V out is basically everything gonna be changed after you pass the signal to the VCO, right? So the VCO gonna have your whole frequency component to be modulated, and it's gonna be like entirely different to your modulated signals. That's the reason why we're using like a different terms. We're using AO and PHIO. And PHIO essentially is 2 pi kV and with the integral of your V tau d tau. So that's like frequency modulations. And then your ST is gonna to multiply with your ST gonna be multiplied with your signal after you go through the VCO. And this phase detector is essentially like a multiplier, and you're gonna multiply it, and you're gonna have a very long expression. And after you go through this loop filter, you're gonna have only this AC over 2 times by sine phi minus phi naught. And we have to assume this sine phi minus phi naught is really small. It's like a logic is because essentially you will minimize this phi and phi naught to be really, really small, right? So you just assume here this value is going to be quite small. And for a small angle, sine phi minus phi naught is essentially just phi minus phi naught, right? Because we assume this phase difference is going to be very, very small, and this value is going to be really small, right? It's assumed to be like a small value. And if it's a small value, then we can say this term essentially equals to this term. And phi minus phi naught is equals to phi e, which is our phase error. And we just do a substitution over there, right? Because phi naught is equals to this term, which is what the VCO does. And we're gonna substitute into this equation, we can get this one. And we're gonna do a kind of differentiation on both sides, and we get this term. And we do like a Fourier transform. Oh, actually, it's not Fourier transform. It's like a Laplace transform, and we can get this term. And if you look at this transfer function, right? Your phase error is gonna equals to 1/1 plus kV times this is the gain of your low pass filter and over JF and times by your phi f, right? Essentially, we want this value to be really, really small, right? Because we want to have like zero phase error. So we want this term to be 0. And if we want to make this value to be quite small, we have to make sure this gain is really big. This gain and this kV to be really big. So essentially, we're trying to make this value and the gain of your loop filter to be really big. And we can minimize your phase error. Does that make sense?
What is phase error? Is it just a shift?
It's like because you know, like when you use the coherent detection, right? You're gonna induce like a exactly.
So that's PLL is just remove that.
Yeah.
phase shift,
Yeah. So essentially, if you increase kV and you increase the gain of the loop filter, you can minimize it because you use like a feedback system, right? Feedback system can essentially reduce the error between like your modular signal and your phase error. You essentially just trying to minimize your phase error.
Sweet, thank you. That makes a lot of sense.
Yeah.
So is KV the amplitude of?
The KV is called frequency. It's called deviation of the. It's called frequency deviation constant, I think. Yeah, it's a term in the frequency modulations. Yeah. So essentially, VCO is just a frequency modulator.
So what's the loop filter do again?
So the loop filter is like, so essentially your modulated signal is just ST, right? So we assume it has a phase error, and you essentially you have nothing here because at the, let's say if t equal to 0, right? You just have your signal go through this phase shifter and go through phase detector and go through loop filter, and then this signal which gonna be modulated by this frequency oscillator. By this voltage control oscillator. So we're gonna do a frequency modulation to this signal, and we're gonna get this signal, and then we're gonna multiply these two signals together to get this expression, which this expression gives you like a phase error. Does that make sense? Yeah, cool. So that's the trick play with like the PLL. Okay, what else we have to cover? I think we can go through the frequency modulation. So the frequency modulation essentially is like an angle modulation. It's like an angle. We'll probably just start another page. So the frequency modulation is essentially like an angle modulation. So angle modulation, we got two parts. We got PM, which is the phase modulation. And we also got the frequency modulation. So what does the PM look like? The PM look like ST is equals to A cos omega MT plus KP. Oh, wait, sorry, it's not omega MT, it's omega CT plus KP MT. And Fn has a form of ST equals to A cos omega CT plus KF with an integral from 0 to tau m tau, actually it's not, from 0 to t m tau d tau. So does everyone have question for the expression for PM FM? I think, yeah, this is on like your lecture slides. So this KP and KF are called, I think it's called phase constant and frequencies. Yes, some name I can't really remember, but it's like some constant, which is, yeah. Yes, yeah, but doesn't really matter. Okay, so it's just two constant you have to put into your expression. And for the frequency modulations, if you want to analyze a spectrum, right, you have to look at what's called a Basel function. A Basel function. So eventually you can rewrite your frequency modulation signal to become as AC with negative infinity to positive infinity, J and beta cos omega CT plus N omega MT. So this is like expression you're gonna to look at if the question asks you to do like spectrum analysis, right? Because we have to use the Basel function. And this beta is like a fixed number. It's in the question kind of gonna give you like if it's equals to 1, if it equals to 2. And this N is like the order. So if you look at the spectrum for the frequency modulation, it would be X, F. So you're gonna have your carrier component, which is J naught beta. And you're gonna have your first order is +1 and -1, which is J1 beta, and which is J -1 beta. And you're gonna have your second order pair, which is J2 beta and J -2 beta, right? And you're gonna have like this order pair to be continuous to infinite. But actually, when it's getting further away from the center, the magnitude of each spectrum gonna be decreased again and again. Eventually, it's gonna be really, really, really small. So if you look at the table, yeah, if you look at the table over there, right, you can see that when your orders goes to like 17, it's like almost goes to 0, right? So you can see it's 0.001, 0.001, 0.001. Yeah, and in the exam, you can use this table to find what is the corresponding value for each order. Yeah, so that's the amplitude spectrum. For the phase spectrum, you have to know that. Okay. Oh, and also for this amplitude spectrum, it's even symmetrical. So these two values are essentially the same. These two values are essentially the same. These two values are essentially the same, right? So we have to make sure that when you got J1 beta, your magnitude essentially equals to J -1 beta. And
What's the beta represent?
the beta is like it's called a Basel constant, and I think that will be given in your question. Yeah, yeah. Also, I think there's a formula for beta. Yeah. Yeah. Actually use FM, use M.
Okay.
Yeah, yeah. So the beta is equals to KF times AM over by omega n. So if the question does not straight give you the beta value, probably just look at those three constant, right? So to see if you got anything about KF, you got anything about AM, you got anything about omega n. And then you can probably just also deduce this beta value. Yeah, I will go through like a problem later on, like you guys will see how it looks like. And for the phase spectrum, oops, like this. For the phase spectrum, because all the value here, right, they are just like a real number, right? Does not have any imaginary part. So essentially, the phase of those numbers just 0, right? Oh, yeah, they are just 0. But if you look at the negative order, especially like J -1 beta or J -3 beta, they have like a you have to have a phase reversal because J1 beta is equals to negative j negative 1 beta. Right? So let's say if your j1 beta is equals to 0.44, then your j negative 1 beta will be equals to negative 0.44, right? So what is the phase of this one? It's just 0, isn't it? The phase is just 0. So how did you express this negative number in the phase? In the complex plane? And essentially, you're doing like 180 shift, right? So the phase of this one will equals to, yeah, minus 180, right? So if the question asks you like to sketch like the phase spectrum, especially when you look at the odd order and also it's negative, you're gonna have like a magnitude of negative 180 for that one. Yeah. Is that clear? And for all and for the rest of them, it's gonna be 0. Because they are just like positive number, isn't it? Does the positive number have any phase value, right? It's just 0, right? So on a complex plane, it's just on this side, right? And if it's negative value, you're gonna have to do like a shift 180 or negative 180. Essentially the same.
So just a question.
Yeah.
Would it be all right if we draw the phase diagram, draw the arrows? It's 180 degrees. So
Yeah, you can also draw. Yeah, you can do like either direction. I think that would be fine. Yeah. Cool. Any question on that? Also, yeah, one more thing to go through is the bandwidth. So for this frequency modulations, because if you look at the formula here, right, you go like from negative infinity to positive infinity. So it seems like you're having very huge bandwidth, but we actually don't we don't use that huge bandwidth. We actually have to set our frequency bandwidth to use this called to use this rule, which is a constant rule, right? So we have to use this formula, which is 2 delta f plus 2b. So the idea is if this is your matched signal looks like, right? And after it goes to like integrator spec, after you put this spectrum into like integrator, you're gonna have a kind of shaped being different, but almost the same, right? The bandwidth is still like negative b to positive b. And when you put into like frequency modulations, right? You're gonna have your FC which being located here and gonna to do FC plus delta F and FC minus delta F for this two section. It's kind of same as like, because the term is cos omega CT plus n omega mt, right? So essentially like you have to do like a shifting of your, you have to do the shifting of your message spectrum, right? To both right side and left side. And eventually you will choose the bandwidth, which is this section. And it goes to 2 delta F plus 2B. Does that make sense? Or you got any question for that? Is that cool? So this is the bandwidth will look like, right? Especially if the question say like you're going to use frequency modulation, you're going to know what is the bandwidth for that. You have to look at the delta F and the beta. Yes, cool. Yes. Okay, so I'm gonna then go through like some past paper exams. Actually, it's from my, I think this question from my term, which doing this course. Yeah. Cool.
Before we go to the
Yeah,
question, quick
yeah,
question.
yeah.
In the lectures, I think the basal function,
Yeah.
basal constant beta, there's also an equation for where it equals to for P for phase modulation. It equals to KP.
Yeah, it's equals. Yeah.
AC, why don't we
Yes,
use that?
KPAM.
We can't use basal function tables for yeah, that one.
Yeah, this one, right?
Yeah, this is only for if we want to.
You can use.
Convert.
Yeah, it's like if the, because like it's normally the question will like, actually I don't think it's gonna be a lot of phase modulation question in the exam, but I'm not quite sure. But it really depends, right? So if the question says it's phase modulation, just use this one. If it's safe, it's frequency modulation, just use this one,
Okay,
this
but-
one, right? Yeah,
Sorry,
depends on
I
question.
misunderstood. Did you say we're not allowed to use basic functions?
You can use,
We
you,
can.
you can. Yeah.
Yeah, so
Cool. Yeah. So this question is, you got a message signal, you got xt equals to frequency component, which is 40 and 90. And it's transmitting using a double sideband suppressed carrier. And with a sinusoidal carrier have a frequency FC and amplitude of AC. And you have to sketch what is the spectrum looks like, right? So for the DSP-SC, the spectrum looks like this, right? You got this pair of your carrier components, but you have FC plus FM, FC minus FM, negative FC plus FM, negative FC minus FM, right? So your spectrum should look like something like this. And because your message frequency is 40 and 90, so you got two components. So essentially you're gonna have like 4 pairs of spectrum, right? You're gonna have your FC, which is yeah. So you're gonna have an FC. Let's say it's FC, right? And you're gonna have which a pair of them will be FC plus 40. And other pair will be FC minus 40. I'm gonna have negative FC, right? It's gonna be negative FC plus 40 and negative FC minus 40. Because you also got another component which is 90, right? So you're gonna have other pair. Oh wait, they should have the same magnitude. Oh wait, they don't have the same magnitude. This one has smaller. So this is gonna be FC plus 90 degrees, plus 90 hertz, and this one gonna be FC minus 90. And this is gonna be negative FC plus 90. It's gonna be negative FC minus 90. That's gonna be your amplitude spectrum. Anyone got a question for that? Yeah. Yeah.
Can you just draw this without doing anything of the calculations?
You can. It's like you just think like this, right? So for your DSP, right? So essentially what we're doing is like you're doing like FC plus or minus FM, right? So here you got two FM component, which is 40 and 90, right?
Yeah.
So it means you generate like 4 pairs, right? You got plus 40, minus 40, plus 90, minus 90 for the positive side, right? For the negative side, you also got
You have to label the amplitude. right?
yeah,
Like
the amplitude, yeah. So yeah, so the amplitude, if you think of that, if you look at the Fourier transform here, right? So we are looking at, if we analyzing in frequency instead of angular frequency, if it's just like a frequency, right? So it's like half. You're gonna half your if it's like cos 2 pi f naught t, you're gonna use like half, right? So this would be, I think this will be AC over, the magnitude is going to be AC squared over 4, and this is going to be, oh, I'm gonna use another color. I think this value is going to be AC squared over 4, and this value is going to be AC squared over 8. Yeah, so the idea of this one is because if you use cos 2 pi 40t, and you're going to multiply with our carrier frequency, let's say cos omega ct, right? So we're going to use the trigonometric identity, which is this one, right? So you're going to half it first. You're going to do like a half first. You're going to have a half cos 2 pi 40t plus cos omega ct and plus cos 2 pi 40t minus omega ct, right? So this is the first half you get. And the second half is when you use the Fourier transform to both of expression. So this one gonna be half like delta f minus f naught plus delta f plus f naught. And this gonna also have yeah, so this will like the second 1/2 comes from. And when you do them multiply together, you got like 4. You got like AC over 4. And the reason why you have like over 8 is because for this expression, you got extra 1/2. And you got like half times by half, which you got 1/8.
Why is
Why
it
is it
squared?
squared?
Oh,
Why is it AC?
yeah, the square is because it has the amplitude of AC, right? So, oh yeah, probably it's not square. Yeah. Yeah, never mind. Because I thought the mass signal should have AC. Never mind. Yeah. Did you guys understand like why it's over 4 and over 8? Because it's kind of like trick, right?
No. I was just
Yeah.
wondering if you needed to do the calculation.
You can do the calculation, but
But you don't
the
do anything.
but during
Okay.
exam is the time is like a little bit short, right? So you want to use some trick to do it quite quick, right? Because when you do like a 2 cosine function, multiply them together, and you're trying to, and first time you apply your trig identity is like you're gonna take like half, and then you apply your Fourier transform, you're gonna take another half. So your amplitude essentially divided by 4 now, right? So it's like AC over 4. And if you look at the second term, you got another half which is here. So you're gonna basically 1/4 times 1/2 again, so which equals to 1/8. Does that make sense?
Wait, where's the 4?
The 4 is from because you got like a half here, right? And then when you do the Fourier transform, you essentially transform like this cos term into this expression half with delta minus delta f minus f naught plus delta f plus f naught, right? So you got another half. So half times half, which is equal to a quarter, right? And then if you have because this time you have another half, right? You just multiply by that half again, which got like 1/8. And that's the reason why it got AC over 8. Does that make sense? Yeah, it's like a trick when you do the question because like this is the first question, right? It's the first question in my exam. So if you want to do like the most, probably the most easy way to express the whole expression, then do the Fourier transform. But I think it's gonna take very long time to do it. So you can probably just use that trick. Does that make clear? Yeah. Okay. And for I think you also need to, for the spectrum, I think you also have to do like the phase spectrum. For the phase spectrum, essentially, yeah, I think for the phase spectrum, essentially, it's just gonna be 0. Because they are just like all like they just have like 0 phase shift value, right? So the essentially just gonna be 0 for all the frequency. Yeah. Got a question for that?
Is that because they're all close?
Yeah, they're all cos term, so they don't have to do anything. And also, there's no like imaginary section, right? Because if the given signal is like sine, then you have to do like 1/2j delta f minus f naught some stuff, and then you got like a imaginary term which cause like a phase difference. But this one like it's like all cosine term, and then also they don't have any phase shifting, right? So we just have like all for the phase spectrum just going to be 0 for all frequency components. Is that clear? Got any question?
So is that what we have to do for question 1?
Yes, pretty much. Exactly. Yeah, but I mean, for this one, it's like the quickest way you can do it. But if you are not quite confident with that, you can just expand all the expression like you're gonna copy this term and then multiply with cos omega ct, then expand it and do the Fourier transform. and then you can find that, right? But I think it's gonna take very long time to do that.
Can you show us how to do the phasor diagram?
Phase diagram, cool. Yeah. So if you look at the phasor diagram, right? Here we got 4 different components and with AC component, with a carry component, right? So for this term, cos 2 pi 40t, right? The way we're gonna do it is we're gonna do half. Actually, it's not half. It's yeah, it's half. So it's gonna be so be negative 2 pi 40 t plus ej negative 2 pi 40 t. Everyone familiar with this expression? So cos omega t essentially is just half e to the j omega t plus e to the negative j omega t. Anyone familiar with this expression? Right? And for sine omega t, it is the difference between 2 conjugate. All right? Is everyone familiar with that? Yes. The phasor diagram is trying to write this one and trying to express this one as a phasor. So how do we express this term? So we're gonna look at separately, right? So how are we gonna express this term on the phasor diagram? It's just gonna be like this, right? So it's kind of a phase difference of 40 degrees. And actually it's not 40, actually it should be 2 pi 40. And with an amplitude of half. And for the negative section, it's gonna be like this. Negative 2 pi 40. I think there's a question. Should be 2j on the bottom of, oh yeah, true. It should be 2j, exactly. Sorry for that. It's gonna be negative half. It's gonna be negative 2 pi over 40, and then magnitude is also gonna be half. Everyone clear for how do you write the first expression into phasor?
What does it say exactly? Is it 2 pi times 40? Or is it
Yeah, it's 2 pi times 40. Yeah. Yeah, everyone clear for the first one? Yeah. And for the second one, which is negative half, it's half cos 90. It's 2 pi 90. 2 pi 90 t, right? So we're essentially use the same trick. We're going to use half times half, and then ej 2 pi 90 t plus e negative j 2 pi 90 t, right? And then it's going to be 1 over 4 with ej 2 pi, and then plus e negative j 2 pi 90 t, right? And then we can draw it as 1 over 4, but with 2 pi 90, and 1 over 4 is negative 2 pi 90. And eventually we can do like a vector addition. So we can probably just shift this vector to here, and we can form this vector, and then we can shift this vector to here, and we got two we got two components which exactly on your x-axis, and this is your vector addition over there. Oh yeah, I will just do it again.
Before you do
Yeah.
it again,
Yeah.
why is the green one further apart from the blue?
It's you can do like at the same spot. Doesn't
Oh,
matter.
right.
Yeah,
It
you
just
can
makes
do,
it a bit
yeah,
clearer.
yeah. You can probably just sketch like that. You can sketch like that. Yeah, but yeah, I just wanted to make it a little bit clear. So you can, and then you can just do the shifting, right? You can essentially shift. Can I use another color? You can shift this one to here, right? So this vector and this vector is essentially the same. And you can also shift. So you're gonna add these two together, you're gonna form this line, right? You're gonna form this vector. And then you can shift this vector to here, right? And you're gonna form another vector, which is both of them are on the x-axis. Is that clear? That's like how you draw the phasor diagram. You have to verify, like, eventually both of them have to be on the x-axis. Okay? Yeah, cool.
Do you have to edit or you don't?
I don't have to edit it, but
Okay.
just yeah, you can verify it anyway. Yeah. Okay. This one is called calculating energy. So consider a message signal which is xt equals to cos 2 pi t, or 200 pi t, which is transmitted using AM. Find the transmitted power st and transmitted bandwidth for this AM modulated signal with underlying carrier amplitude of 10 and with a modulation index of 0.6. Okay. So does anyone of you guys know how to find the energy for like a signal? What's the formula for that?
Amplitude squared.
Yeah, exactly. Mp squared onto. The reason for it is mp squared onto is energy is equals to 1 over t from 0 to t and st modulus square dt. So that's the equation for how you calculate energy. But here you're assuming it's like a sinusoidal function, right? So we can write it as to cos omega, probably cos omega m square dt. And you can rewrite it as half 1 plus cos 2 omega mt dt. And yeah, I think there's it should be like an amplitude over there. Should be a. It's gonna be a squared with this term. And if you integrate like a cos term over there, it essentially just equals to, it essentially would just be equals to t. So you're gonna write it as a half times 1 over t, and essentially when you're doing this term, 1 plus cos 2 omega mt dt. So this term will eventually get to t, and then you're gonna to have a squared over 2. So you don't really have to like to go through this derivation or exam. Doesn't really matter. Just want to make sure that you guys know that when we consider about sinusoidal function, right? So if you know that your input signal gonna be like sine function or cosine function, then your energy gonna straight to be a squared over 2, which is amplitude squared over 2. And this is what we're gonna do for this question.
Can you assume that's always going to be the case?
If it is sinusoidal function, if it's like sine function or cosine function, then you can use it. Okay, so what's the modulus signal for your ST? It's AC times by 1 plus m cos omega mt and times by cos omega ct, right? And we're gonna do some substitutions. So your AC is gonna be 10. It's gonna be 1 plus, which your modulation index is gonna be 0.6 cos omega t times by cos omega ct, right? Your omega m is just 200 pounds. Never mind. So you're gonna have. So we don't really, in this question, we don't really have to care about what's in the frequency, because we won't look at amplitude, right? The idea to calculate the energy is like we have to use amplitude squared over 2. So inside, so what is the actual frequency doesn't not really matter. we're gonna do plus 6 cos omega mt and times by cos omega ct, right? And then we can do 10 cos omega ct plus 6 times by cos omega mt times by cos omega ct. And then we can apply the trig identity. It equals to cos omega m plus omega ct and plus cos omega m minus omega ct. Anyone got a question from this step to this step? So essentially we just apply like a trig identity over there. Any question for that? Okay, so essentially if you look at right now, you only got 3 sinusoidal functions, isn't it? You got 3 sinusoidal sections, right? So what's the energy for this one? If I plot a squared over 2, this one would just be 100 over 2, which is 50. Oh, wait, it should be 10 over 10 squared over 2, right? Which is essentially 100 over 2, which is 50. Got a question for that? Oh, cool. Yep. What about this 2 section, right? These 2 have the same amplitude, which means they are having the same energy, right? So what's the energy for that? So the amplitude will be 3, right? The amplitude will be 3. Then 3 squared over 2, which is 9 over 2, right? And because you got 2 exactly, because you got 2 signal exactly the same energy, you're going to multiply by 2 again, which is 9. So if you add them together, it's going to be 50 plus 9, which is 59. Yeah. Good. Yeah. Yeah.
Can you just find you're given the modulation index,
Yeah,
right? Can
yeah.
you just use that formula?
Which formula?
The formula that they give in the lectures where you calculate.
Oh yeah, you
power
can,
and,
you
like,
can,
straight away
you can,
comes
you can,
from
you can also do that.
instead of, like, doing
Yeah,
all that.
yeah, you can also do that. Yeah, because yeah, true. You can also use the lecture slides formula to do that. Yeah, but either way you can do it. Like, yeah. Any question for this one? Okay. Okay, so this is a really trick question for that year paper. So it seems to be really complicated, right? So you got a very complicated XT, and then you're gonna like do addition with a local oscillator signal, which is cos omega CT, and you're gonna fit into like a nonlinear elements block and have a V out. And you're gonna pass through like a low pass filter, and then you're gonna find what is the range for this field. So this question looks like to be really tricky. And then there's a trick to do this question, right? Because everyone sees this question, the first intuition they're gonna think is I'm gonna to write down expression and then I'm gonna plot. So what the majority of people do is like they're gonna do like half cos 2 pi 70t plus 1 over 3 cos 2 pi 120t, right? And then they're gonna do the addition with this cos omega CT. And then, so this is your input, right? So this is your V in. Because the output is in the form of A times by V in plus A2 times by V in squared, right? And then everyone just trying to, do the square of this whole expression and times by A2 constant and plus A in and times by and plus by like A1 times by V in. So it's gonna make the expression very long, and also it's really hard to, it will make this question become very hard to do, okay? So this is a trick. So you don't have to express the xt into its real form. You can just write it simple as xt. So so your V input in this case would just be xt plus cos omega ct. So this would be V input, and your V output will be A1 times xt plus cos omega ct and plus A2 times by xt plus cos omega ct squared. Right? Because you know that's the V, right? That's being given by the question. And your V out is just is also being given, right? It's A1 times V plus A2 times V squared. So this is V squared. Yeah. Anyone got a question for that? Okay. Yeah. And also in the question it says, this output from the filter is a standard AM signal. So what does a standard AM signal mean? It means it's gonna be in the form of AC times by 1 plus n cos omega mt times by cos omega ct, right? So this is gonna be like a standard AM signal. So what we're gonna do is like you're gonna expand this whole expression, and then you're going to match the expression to this term. Yeah, you guys will see how it goes. Okay, so let's do expansion first. It's going to be a little bit annoying actually to this expression, but I think that's the most straightforward to do this one. So you're going to do A1 times xt times y plus A1 times omega cos omega ct, and then A2 times by x squared t plus 2xt cos omega ct and plus cos squared omega ct, right? You're gonna expand the expression. It's gonna be cos omega ct plus a2 x2t, and then 2xt cos omega ct plus actually 2 times by 2xt omega ct, and then plus a2 cos squared omega ct. Right? So we just do expansion and expansion. Any question about this? Right? We just do expansion, right? And then because this is our V out, right? So essentially, this is what we should get at the output of the filter, right? But the question says we want to have a very standard AM signal. So we want to make sure that this output will have exactly the same format as this one. So what does this one looks like? This one is essentially just AC cos omega CT plus ACN cos omega MT cos omega CT, right? So essentially this output would be in this format, right? And we want to make sure that this expression that we get should follow exactly the same format of this one. These two should have exactly the same format, right? But apparently right now we see a lot of different terms over there, right? It's more than like these two terms. In this expression, you only got two terms, right? But in this expression, you got 1, 2, 3, 4, 5. You got like 5 terms, right? That's the reason why we use a filter here, right? We're trying to use the filter to get rid of. We're trying to use this filter to get rid of the component that we do not want, right? So if you try to compare these two terms, which term is the one that we desire, right? Which of the terms is the one we want? So AC cos omega C, yeah, these two looks the same or looks similar, right? So which means this term is the one that we want to keep. And if you're looking at this term, AC times cos omega N times cos omega C, so which one looks like that? This one, right? Oh, oops, sorry. Yeah. So these two green terms, they look similar, right? And that's the one we want to keep. These two blue terms, they look similar, right? This is also what we want to keep. So all the rest, the terms, we want to get rid of them. And that's the reason why we're using this low pass filter, right? We're trying to use this low pass filter to get rid of this term, and this term. because we don't want them. Because the question say we want a standard AM signal at the output of filter, right? So this is the signal we kind of get at these stages, right? At these stages, this is a signal, V out, right? And after it goes through a specific filter that we design, we can get rid of all these three terms, which being left with these two terms. Anyone got a question for that? All good? Yeah.
Can you zoom out a little bit so I can take?
Yeah. Yeah. Okay, so the question asks you to find A1, A2, right? So if we want to find A1, it essentially just, because these two green terms, like they are matching to each other. Oh, I think I should make a little bit smaller, otherwise you guys cannot see the process. Oh, no. So essentially we want to make sure that AC and A1 are exactly the same, right? Because we wanted to keep these two terms. So AC gonna be equals to A1, right? So what is the AC? The AC is given by 10, right? So A1 is just equals to 10. So to find A2, we're using the same matching methodology, right? So we want to make sure that ACN is equals to A2 times by 2, right? So we're using like the same methodology and then we can find A2, right? So in fact, essentially what we want to do is to do the term matching and then we can use term matching to find the coefficient. That's the idea, right? Everyone being clear with this question? Okay. Yeah, because like I think we're kind of probably gonna run out of time, so I'm gonna be a little bit quick for the next few questions. Okay, so I'm gonna do this frequency modulation question because I just say I'm gonna show like how does this spatial function actually gonna works in a real question. So in this question, it gives you like a beta value, right? So if you guys remember, the frequency modulation signal looks like AC times by negative infinity, positive infinity with J and beta. And then times by cos omega mt. Oh, oops, it should be cos omega ct plus n cos n omega mt, right? So that's going to be the expression. And right now, because the question gives you like the beta is equals to 1, so it's just going to be 1. Does that make sure? Does that make sense? Because it's been given like beta is equal to 1. So you just simply replace beta with 1. Right? And if you look at the table, right, we can just look at this line. Because that's all the information that we need. Right? This line is like beta equals to 1, right? So this column has all the information that we need. 0, 1, 2, 3, 4, 5, 6, and up to 17. But we don't have to use that much data. And FM is equals to 100 Hertz. And then, okay, so this is a very important information. An ideal bandpass filter of bandwidth B equals to 205 Hertz centered at 500 Hertz, right? So this frequency modulation signal is gonna go through like a low pass filter and it's gonna block a lot of frequency component. The reason of we use like a filter is like we're trying to get rid of some frequency components. So what kind of frequency component we're going to get rid of in this case? Because the low pass filter looks like it's centered at 500 and with bandwidth 250, so it's going to be because the length of this width is 250, right? So this is going to be 500 plus 250 over 2. This is going to be 500 minus 250 over 2. So this is going to be your bandpass filter. Yep. Cool. So yeah. So this is how the band pass filter looks like. Everyone clear with that? Right, because it says send it at 500 hertz and then got a bandwidth 250. So the upper limit of this band pass filter is going to be 5 plus 250 over 2, and the lower limit of this band pass filter is going to be 500 minus 250 over 2. Right? Okay. So yeah, so I think so what's the frequency would be that? It's 500 plus it's gonna be 625 and this is gonna be 325, right? If I'm not doing my calculator wrong. Oh, 375. Yeah, thank you. Yeah. So only the frequency that within this range will be considered in this case. Any frequency out of the range will not be considered, okay? So we're gonna just see how many frequency components are gonna be involved this time. Because our message signal is 100, right? Our message signal is equals to 100 hertz. And if you look at this term here, what is the center frequency? Is 500, right? Fc equals to 500. So we're gonna try for each n value. We're gonna try for each n value because this n is basically from 0 to like 10 or 11, doesn't matter. We're gonna try for each of them and to see if this frequency is still within this range. So if n is equal to 0, so it's gonna be Fc plus n Fn, right? So if n is equal to 0, this term will just equals to equals to 500, right? So 500 is definitely within this band pass filter. So we're gonna put a tick over there, right? When n is equal to 1, what's the value gonna be? 500 plus 100, right? Because n is equal to 1, Fm is 100, and Fc plus 100 is just equal to 600. Is that in the range? Yes. So we're gonna take a tick for that one, right? It's 600, also in the range. And because n equal to 1 works, it also works for n equals to -1, because just as I said before, this frequency spectrum, they are symmetrical, even symmetrical. So if exists for n equals to 1, there must be another spectrum for n equal to -1. And we're gonna try for n equals to 2. So if n equals to 2, it's gonna be 500 plus 2 times 100. So what's gonna be? It's gonna be 700, right? So is 700 inside the band pass filter range? Right, it's not, right? So this component will be blocked. So we don't have any frequency component beyond n equals to 1. So n equals to 2, 3, 4, 5, 6, 7, 8, 9, 10, until like whatever. Those frequency components are all gonna be blocked. So we're only gonna have 3 components, n equals 0, n equals 1, and n equals to -1. Right, so those are the only 3 components we're gonna be left with. So how does this frequency spectrum gonna look like? It would be, we got the n equals to n case, you got n equals to n cases, you got n equals to 1 cases, you got n equals to -1 case, right? And what are the value for them? When beta is equals to 1, n equals to 1, it's 0.77, isn't it? So this magnitude is going to be 0.77. What about beta equal to 1 and equals to 1? It's going to be 0.44, right? If you look at the table. So this value is going to be 0.44 because they are even symmetrical. This one is going to be 0.44. So that would be the frequency spectrum looks like. And the rest of the frequency components they get all blocked by the band pass filter. So we're not gonna show them on the spectrum. Yeah, and also, so how does this frequency modulation signal gonna look like? The frequency modulation signal is different to amplitude modulation. The amplitude modulation, we got amplitude increase, right? For the frequency modulation signal, we got frequency. So the frequency modulation signal look like this. So it look like this. So if we say we got a period t over here and another period t over here, we got 2 frequency operated So at this period, the signal operate as a frequency 1, and this period, the frequency is operated at the frequency 2. So this frequency 1 will be, this frequency 1 will be 500 minus 100, which is, F1 will be, actually F1 will be 500 plus 100, which is 600 Hertz. And F2 is going to be 500 minus 100, which is equal to 400 Hertz. Because we are only allowing when you have n equals to 1 and n equals to, because you're only allowing these cases, right? You not have like two, you not have any order like above 1, like n equal to 2 or n equal to 3. So like you're essentially just using 500 plus 100 or 500 minus 100, right? So that's the two frequency modulation frequency that you have, right? So you're having one period with 600, another period with like 400. So that's how like the frequency modulated signal looks like. And for the rotation phasor diagram, you got n equals to naught, n equals to plus or minus 1, right? So when this one is equal to, when n is equal to 0, you only look at your carrier component, which is, I'll just gonna call it AC. And when n is equal to 1 or negative 1, we just say n is like an odd number, right? We're gonna have the phasor look like this. And this is 0.44, 0.44. And this green section is 0.77. And if we do addition of these two odd phasor, we're gonna form a signal like this. So let's say if this V1, V2, right? So this is just V1 plus V2. And you will find the resultant of these two odd phasor is gonna be perpendicular to your carrier component. It's gonna be 90 degrees phase shifted to your carrier component. That's for the odd. The odd resultant is gonna have 90 to 90 phase difference to your carrier. Okay, so let's say if we have n equals to 2 in this case, right? We allow n equal to 2 in. We do not use band pass filter. We're gonna have another phasor look like this. So this is your n equal to 2 case. This is your n equal to negative 2 cases. And the resultant is going to look like this. And you will find this resultant is exactly in phase with your carrier frequency. Because they are parallel, right? They are not having like a 90 degrees. And this is essentially what I talked about in the Basel function previous, is this one, right? So when you look at the negative or the positive even number cases, they all have like 0 phase difference. So that's the reason why they have the same. But if you look at the odd one, right, they go like negative. They go exactly flip it. So that's the reason why I got like 90. Yeah.
What are the angles of the two sides
Which one?
of 0.44? Is it just 45 degrees?
Yeah, pretty much.
Just all 45 degrees?
Yeah, I think so. Yeah, actually,
The perpendicular to the
yeah.
0.44.
Yeah, and you have to make sure that your even resultant is in phase with the carrier. Yeah, all resultant is 90 phase difference. Like you can see this line, this green line, that like they are 90 degrees, right? But these two lines like they are parallel. These two resultant vectors, they are parallel. So that's how you draw the phasor diagram. Actually, it's called rotation phasor diagram. Oh, oops. Okay. For the last question, which this term question, we're gonna look at these two formula. Actually, it's a comparison between PM and FM. So we're gonna look at specifically like how does the beta value gonna affect your frequency spectrum. So for the PM, your beta is just equals to Kp times by AM. For the FM is equals to Kf times by AM and off over the FM. Yeah, actually it's FD. So for the part A, it says the tone amplitude increase or decrease. So what will the tone amplitude increase or decrease eventually cause effect to your output spectrum? So for part A, because you only look at your tone amplitude, which is an AM value, right? So you are not change your frequency or whatever, right? So you only change like your AM. So this will only cause your tune amplitude to be increased or decreased. But the line spacing, so the line spacing, like, right? So those are the line spacing, right? They are not changes. You only change like the amplitude of the tune, right? Because the AM is the only factor. You're gonna affect this spectrum, right? So you're not changing your line spacing, you only change your amplitude of the spectrum. For part B, it says the tone frequency is increase or decrease. So how does the tone frequency increase or decrease gonna affect two spectra, right? Because this time you change your tone frequency, definitely your line spacing gonna be changed, right? Because think about it, right? If you have your tone frequency to be different, each spectrum gonna be separated or be closed, right? Depends on your increase or decrease of tone frequency. But your line spacing definitely gonna change this time because you're changing your tone frequency. So your line spacing gonna be different. Line spacing will be different, right? So essentially is this width is gonna change this, right? It's sort of like this, right? You're having essentially like initially you have a greater line spacing, but now you're gonna decrease, right? It look like this. Your line spacing gonna be different. So what about your amplitude? What about your spectral amplitude? The spectral amplitude will only be affected by your FM. Will only be affected by FM. The reason is if you change your tone frequency, right? If you change this one, so let's say if this one is decreased, if this value is decreased, and your beta is constant, right? If you make sure that beta is like keeps and not changing, right? But your frequency, your tone frequency is decreased, then you have to make sure that AM is increased because this is a constant, right? If you decrease this one, you have to decrease your AM. You have to decrease your AM as well because you have to make sure this beta is not changed. But for your PM, it does not really matter, right? Because this beta does not involve any term of FM, does not involve any term of your frequency tone frequency. But your FM involve a term which had the tone frequency. So if you change your tone frequency, which was FM here, if you want to make sure that your beta is constant, you have to change your AM as well. So your tone amplitude will be affected in this case. Yeah. A question on that? Okay. And for the part C, right, you got the tone amplitude and frequency of both increase or decrease, but in the same portion, right? So your line spacing, of course, gonna be affected in the same way because your tone frequency changes, right? But this time it says that your amplitude and frequency are being increased or decreasing the same portion, which means you are literally increasing and decreasing these two with the same portion, right? So increasing the same portion and also you're decreasing the same portion. So this beta will be not affected anymore. So your line spacing will be changed. And your amplitude is also going to be changed as well. Any questions? And for the last question, I think, so this is just one more question. So for the low pass filter, essentially it's just gonna, because this is using a derivative block, right? And also, you're gonna have like a sharp waveform. So this low pass filter essentially trying to smooth the sharp edges and get rid of the high frequency component. And that's it for the last question. Yep. Because it's one mark, you can totally just write us about like get rid of the age or something like that, and that's it. Yeah, I think is like another group gonna come in outside. So yeah, yeah, yeah. I think it's 4 now. So yeah. Yeah, we'll finish. Yeah, you guys got any question for this one? Or just gonna end it?
I'm not sure if you're able to answer this, but
Yeah.
it's more on the structure of the test.
Yeah.
It's 5 questions.
So
what do you think the first 2 will be on?
Actually, this year you guys gonna be in different format, right? I think it's gonna be level 1, level 2, level 3, level 4, level 5. I have no clue about how the exam question gonna be, like the difficulty. But apparently, level 2 gonna be the easiest, right? I think level 2 gonna be like how you do the very simple spectrum, right? How does the AM spectrum look like? How does DSP spectrum look like? And for like level 5 question, probably gonna be, the trick question I talked about, right? You have to do some tricks and do the matching coefficient. So I think that would be like level 4, level 5 question. Yeah, and yeah, pretty much because like you guys exam gonna be in completely different format.